So, oxidation of alcohols. So first thing we want to look at, if we can oxidise an alcohol, is our oxidising agent. And this is acidified potassium dichromate. Potassium dichromate, K2Cr2O7. Quite often see that abbreviated, so we'll miss the potassiums out. If you're asked for the reagent, keep the potassiums in, but you'll often see that just shown as the dichromate ion. Again, we need to mention the acid, so you can either say acidified or we can quote the acid that we're using, which would be sulfuric acid. Again, you'll see that abbreviated as just H+. Potassium dichromate is a lovely orange colour. So when it starts off, the solution, there we go, is orange. And we can see that it's working as an oxidizing agent. As the alcohol gets oxidized, the chromium gets reduced and goes a greeny blue colour, showing that we've made chromium 3+. So the chromium has been reduced, there we go, from an oxidation state of 6 to 3. We should be able to put this half equation together. First of all, making sure that we balance the chromiums. Then we need to balance the oxygens by popping 7 waters on the right hand side. Sort the hydrogens out, so that means that we've got 14 hydrogen ions on the left hand side, and then we just need to do the charge, so we've got 12+ on the left, 6+ on the right, so that leaves us overall 6 electrons on the left hand side. So, oxidizing primary alcohols. See, it's a primary alcohol. That carbon's bonded to 2 other hydrogens. So if we're oxidizing a primary alcohol, in the first instance, this is what we get. So we concentrate the amount of oxygen on the carbon, and this is an aldehyde. So carbon double bond oxygen with a hydrogen is an aldehyde. This carbon double bond oxygen is known as a carbonyl group. We'll be seeing those quite a lot. And you can spot that it's an aldehyde because attached to that will just be 1 hydrogen, which means that we're able to oxidize an aldehyde further because we can get more oxygens attached to that. This group we'll probably recognize as a carboxylic acid. So primary alcohols can be oxidized to aldehydes, which can in turn be oxidized to carboxylic acids. Now I think this is a little bit like boiling an egg. So when we boil an egg, if you just boil it for a few minutes, you get a soft boiled egg. But if you oxidize it further, if you cook it a little bit more, then you end up with a hard boiled egg. So the soft boiled egg is like an aldehyde, so we just want to give it a little bit of a reaction, but if we're not careful, then the aldehyde will turn through and turn into a carboxylic acid. These are the conditions then for making an aldehyde. This is where we need to only react slightly, so we don't want it to leave it reacting too long. So we'd start off with our primary alcohol in the flask there, along with our oxidizing agent, and we would give this just a small amount of heat. We'd be able to see that the reaction was started by the oxidizing agent changing from orange to green, and our alcohol is turning into an aldehyde. Now these have got different functional groups. You can see that the alcohol with the OH would have hydrogen bonding, whereas the aldehyde doesn't have hydrogen bonding, would just have dipole-dipole, so would have a significantly lower boiling point. That means that with gentle heat the aldehyde will evaporate first. So as soon as you start this reaction, the aldehyde starts evaporating. There's nowhere for it to go, so it reaches the condenser. Now the condenser is a tube that's surrounded by cold water, so you put some cold water in from the tap at the bottom there and force water up through the condenser and take your cold water out. So this is always cold. It will condense the aldehyde vapor back into a liquid, and that would trickle down the condenser, and then you'd collect it at the end. So that's making a soft boiled egg. If you want to make a hard boiled egg, the carboxylic acid, then this is a lot easier. So this apparatus is known as refluxing. So you put the condenser tube vertically. There's no lid at the top of the condenser. There's water in, water out. So react the alcohol with your acidified dichromate. In the first instance, you'll make an aldehyde which will try to escape, so it's going to evaporate, but it reaches the condenser, turns back into a liquid, and then falls back into the flask and continues to react. So your primary alcohol will in the first instance make an aldehyde, but you're not giving it chance to escape, so it will continue to react, make a carboxylic acid. So we'd leave that in there for a good 20 minutes, 30 minutes, and give the aldehyde chance to fully react and make a carboxylic acid. In terms of the equations that we'd write to show these oxidation processes, including our acidified dichromate, it's quite complicated. So to make life easier, just to show our oxidizing agent, we'll show the oxygen that provides by just using an O for oxygen, but we're just putting it in square brackets, which is essentially putting it in quotation marks. So there's ethanol reacting with some of the oxidizing agent. And remember, this is a primary alcohol, so we're going to go to an aldehyde first, and there's ethanol. We can see that reaction's not balanced. So water is the other product. That is now balanced. Remember that the ethanol will oxidize further to make our carboxylic acid. So with 2 carbons, that's just going to give us ethanoic acid. And you can probably see that that's now balanced, so no other products needed. You can do these 2 processes combined, so going straight from the ethanol to the ethanoic acid. As an equation, that now means that we need the 2 oxygens altogether, as well as the 1 water that we had in the first step. So that's the balanced equation for the oxidation going all the way through. Secondary alcohols can also be oxidized. So there's a secondary alcohol. We've just got 1 hydrogen attached to the carbon, which means we can increase the amount of oxygen on that carbon, like making the aldehyde. We've got the carbon double bond oxygen. These are now known as ketones. So if you see a carbonyl group central to a chain, then we've probably got a ketone. Ketones can't be oxidized any further. So oxidizing propan-2-ol, so that carbon is going to turn into a carbonyl group. Let's have a look. So there's the carbon double bond oxygen, and that's the simplest possible secondary alcohol. So this is the simplest possible ketone, and this ketone, 3 carbons, is known as propanone. We'll have a look at the carbonyl group in more detail. So I've drawn it out a little bit better here, showing its correct shape and geometry. So a very important group in organic chemistry. The shape, as you can probably see from how I've drawn it, is trigonal planar, which means the bond angle is 120 degrees around that. The oxygen more electronegative than the carbon, so it's a polar bond, which leaves them susceptible to nucleophilic attack because the carbon's electron deficient. What do you do with tertiary alcohols? Well, we can't really intensify the number of bonds on that carbon to oxygen, so you can't oxidize tertiary alcohols.